Hello everyone, we are the group number 5 and today we will present our midterm project for years. My name is Eric Solórzano and I will begin with the introduction and objective for our work. So to start, this project focuses on mobile robotics, especially on differential drive robots. These robots move using two independent wheels, so understanding their kinematic is essential to predict how they move in the environment. Odometry is one of the key tools for this. It allows the robot to estimate its position using only the wheel encoders. Even though it's a simple and widely used, it also accumulates errors over time, which makes it important to study and evaluate its movements. For our project, we worked with the LEGO EV3 robot and MATLAB to implement its kinematic model, computed its odometry, and executes the predefined pie-shaped path. The main objectives were to understand the differential drive kinematics, implement the odometry equation, and program the trajectory, and finally visualize and analyze the robot's movement on the MATLAB tools like the plotters or the sourcing code.
Hi, my name is Patricio Vázquez, and I will talk about the methodology that we use in our project. First of all, we describe the physical characteristics of the robot, including the wheel radius, the axle length, and the basic mobility constraints. These parameters are essential because they define how the rotation of each wheel translates into motion on the XY plane. Next, we apply the cinematic model of a differential robot. Using the standard equations, we relate the linear and angular velocity of each robot to the angular speeds of each wheel. After that, we implement the cinematic equation directly in MATLAB. The code was organized into blocks. We first configure the motor and reset the encoders, and then we calculate the wheel speeds required for each commanded motion. Finally, we defined the desired trajectory. In our case, was simplified 5-shape figure. To achieve this path, we programmed 5 movement phases, 2 stretch segments, 2 90-degree rotations, and finally a curved motion. By recording the robots both throughout the execution, we were able to reconstruct and plot the entire trajectory in MATLAB. This methodology integrates the physical model, the MATLAB implementation, and all the real encoder data to evaluate each stage of the robot motion. Thanks.
Using MATLAB and the robot's kinematic model, the LEGO robot correctly followed the plane strain segments. Second, the trajectory reconstructed through the odometry was less accurate, although the physical movement matched the index shape. The odometry-based plots show distortion, especially during transition between motion segments. And the last point is the small errors accumulate for limitation of normal odometry. Different factors such as wheel slip and encoder resolution cause rather post-estimation drift, resulting in a plotted path that differs slightly from the ideal trajectory. Then we have analysis. The first point is that there is a clean difference between physical motion and odometry-based estimation. The robot moved correctly, but the trajectory reconstructed from the encoder data show distortions, demonstrating that odometry alone is not fully reliable. Second point is that odometry errors arise from factors such as wheel slip and encoder resolution. This means that wheel slip creates no systematic errors during turns, while low encoder resolution leads to quantization effects. Both contribute to accumulate drift and inaccurate the estimated path. And last point is that several strategies can improve odometry performance. This can be improved in changing mechanical precision using smoothed motion strategies like gradual curves and integrating additional sensors like a MPU 6050, reduce odometry drift and improve post-estimation.
I am Mario Viteri, and I'll talk about conclusions and recommendations. We have three main conclusions. The first one is that we can prove the mathematical model in order to program desired trajectories of the robot. The second one is that we could use MATLAB plotting tools to visualize clearly the resultant trajectory, meaning that we can easily identify errors or deviations on the trajectories. And the last one is that this practice successfully integrated an encoder readings and computation of the robot's odometric trajectory in real time, which provide us with the results that we later analyzed. And as recommendations, we have that it's desired to be done this practice in a controlled environment. This means in an optimal surface that prevents slippery, for example, and also that it's recommended that we are as accurate as possible with the measurings of the distance of the robot to prevent any errors on the model. Thank you for your attention.